My name is Tianyi Zhao, and I come from the university at North Carolina. And it's my honor to be the first speaker here. And this talk is my first time to give a talk in the workshop. Thank you. And the topic today is this one: is leveraging multi-layer deep features for large-scale visual recognition. And this is my outline. First, I will introduce my problem. The problem I faced is called cost-to-find visual recognition, and this problem is also a top-down hierarchy classification problem. This problem is a very important problem, especially when we have a very large data set. So when the data set is as large as we have thousands or even tens of thousands of image classes, at this time, if we use a hierarchy classification, we can save more time and we can save the computer resource. As you can see from the feature, to solve this problem, we should have a tree first. This is a tree that has a physical meaning. And to solve this problem, first, if a new image came, it will reach the root node first. And the root node will have a classifier to classify this new image to the most possible children node. And at this level, I call it a cost level. And this node will classify these images into the next level, and it will go to the leaf node. So until it goes to the leaf node, we will repeat this process again and again. So this is a problem, and our motivation is this one. Now the deep network is very popular, and there's a lot of discussion about the transferability of the deep network, especially for the most famous AlexNet. So in this figure, the first row is the AlexNet. It has 5 convolutional layers, and it has 3 fully connected layers. And normally, it uses the last layer to classify the images. But you can see from the picture, somebody has already visualized the mid-level output of this network. There's some experiments have shown that the output of the mid-level is common, and the output of the final level is more specific to a particular task. So our idea is to use the common output for the course level classification. Because this property is same as our hierarchical problem. Our hierarchical problem uses a more common feature to solve the course layer problem. And if this idea works, there's one contribution is that it can give some reasonable meaning to the mid-level output of the deep network, because we all know that the deep network is a black box. So if we can give some meaning to the mid-level output, there will be some contribution. Okay, after the motivation, let me introduce our proposed method. First, I build a visual tree instead of use an existing tree. Compared to the WordNet, the visual tree is built by the clustering method on one image features. This one, compared to the WordNet, it not has some physical meanings for each node, but it can maximize the inter-class distance and minimize the intra-class distance. So this one will benefit the classification process. This is a traditional visual tree, and our visual tree is a little bit different. We use the different image feature to build this tree, and you can see from this feature. The node in the blue box use the feature set 2, and the node in the red box use the feature set 1. And all the features come from the different layer in the deep network. So and for each node, the feature is selected by the following formula. The formula means that if the feature set has less intra-class distance, then this feature will be selected for a particular node. After we have this tree structure, we deploy a multiple layer as multitask SVM classifier. The difference between the traditional SVM is that multitask classifier has a common prediction function to the classifier. Our visual tree has provided a good environment to identify the interrelated learning task automatically. So you can see from this formula, the difference is the W0 here. It is called the common prediction function, and this function can be used to characterize the interclass relationship. And this W0 is shared among all the SVM classifier under the same parent node. So far we have the tree and we have the SVM classifier. There is one extra step to increase our accuracy, and this one is called soft prediction. Soft prediction method is to keep more possible children at each node and finally choose the most possible path. In my experiment, I will choose 2 children on each node when the probability of the second children is more than 80% of the first children. And if the image reaches the leaf node, and if we have multiple paths, I will use the leaf node probability to choose the most possible path for the result. Okay, so the final step of our method is called joint learning. Before this, we learn the tree, and we learn deep network and the classifier separately. So there's one possible way to jointly learn these 2 together. The method is to fine-tune the network by the sum of the loss function. In experiment, we deploy the AlexNet training manner. We use the SGD and we use backpropagation. The difference is that we do not have only one loss function. We have a lot of function. We have one loss function for one node. So we use the sum of all the loss function as the one loss function for the backpropagation process. And it's worth noting that the loss functions are based on the different input. Some are based on the mid-level input. Some are based on the final input. So due to the backpropagation, for each loss function, the SGD method will only change the parameter before that loss. This can give a good result that some coarse loss will only affect its earlier parameters. So it will remain the mid-level output common and remain the final output specific. So this is overall method, and due to time limitation, I will show you one result from my experiment. I do this result on the ImageNet database, and it has 1,000 categories, and each category has more than 1,000 images. And the best result comes from the joint learning method, and the second result comes out by learning the deep network and the tree classifier separately. And the third one, I use only the final output to do the tree construction and the classifier learning. And the final one, I even use another tree construction method. It's called label tree to build the tree. Okay, in the summary, first in our paper, we bring the idea that the inter-output of the deep network could be used for cost-to-find classification problem. Then we deploy the multitask SVM classifier, which can characterize the interclass relationships. And finally, we joint learning the deep network and the tree classifier in an end-to-end multi-layer fashion, and we have a better performance. In the future, there's a drawback in our work is that we have to have a tree before the training process. So next step of our work, we will use the unsupervised learning method to joint learning the tree and the classifier together. Thank you.